Click the bell icon to get latest videos from Ekeeda.
Hello friends, now let us solve one more question on standard Turing machine. Over here, we are given with a question where we are supposed to compare two numbers and find out x is greater than or equal to y or not using a Turing machine. We will consider the number is given in the form of unary numbers. Let me start with an example. Over here, I have taken two numbers, x and y. X is taken as unary 4. Y is taken as unary 5. First, let us see how these numbers are represented in the tape of Turing machine. Imagining this is the infinite length input tape for the Turing machine. There would be some blank region over in the left, similarly onto the right. Now we'll consider that initially the Turing machine is set to the point where the first number starts. The first number starts over here. Turing machine would be set to the point where I'm indicating an arrow. So this number x represents over here. So this number x is represented before the number 0. Number y is represented after the number 0. Now the Turing machine has to compare these two numbers and go to any one of the states which represents whether the numbers are greater or equal or less. Over here, whenever x is greater than or equal to y, we need to make that particular state final. Otherwise, x is less than y. In that case, that state would be non-final. Let's start with the construction of the machine. First, let me discuss the idea. The number x would contain some number of ones. The number y would contain some other number of ones. What I will start? With every 1 in the number x, I will swipe out 1 1 from number y. That means I'm basically comparing x and y. If both of them contain equal number of ones, they would terminate at the same time. Whereas, if any one of them contains more number of ones, the other would be not having that many ones. Basically, we are comparing the number of ones. Over here, I'm using some symbol x, which will replace 1. With every 1 from the number x, I will be removing 1 1 from the number y. Whenever they have equal number of ones, they will terminate simultaneously. Whenever x is greater than y, then x would contain some extra ones. Whereas when y is greater than x, then y would contain some extra ones. What I will do is, I'll replace x with every 1 of the number x. Similarly, I'll use an x to represent every 1 in number y, which I am comparing simultaneously. Any one of them is containing an extra one, I would encounter that later. Let's start with the construction of the machine. Over here, I'm declaring Q0 as the initial state. We have considered that initially the Turing machine is set to the start of the first number, that is x. Whenever I read that first one, I'll make it an x and move to the right and move to the next state over here. One is replaced with an x. Along with that, I am moving to the right. Now, after whichever one is coming in the number x, I have to ignore them. For that, we include a loop. The number 1 would be kept as it is, moving to the right. Till what point this will continue? This will continue till the first number is finished. How do we recognize that the first number is finished? We have 0 as a separator between the first number and the second number. whenever we encounter 0, we keep the 0 as it is and move to the right. Let's say the new state is Q2. If we have crossed some number of 1s in the number y already, then those 1 would be replaced with symbol x. We need to skip those symbols to find the first one in y which is not marked yet. So we need to put a loop for replacing all the x with x only. Now, once we encounter a number 1, we can start going left back by replacing the 1 with x. While going back, we need to ignore all the x's and keep on going left. After passing all the x's of the second number, we will reach the point where there is a 0. When we pass that 0 and go to the left, we are reaching at the place of the first number. If the number which is there in the first is not completely swiped out, then there would be some remaining ones. I need to skip through all those ones and reach to the first one. This transition would do that. In fact, this will even replace the first one in the number with 1 only. But I need that one. For that, whenever I reach x, I'll move once again to the right. This entire loop would do the work of comparing the number of 1s in the first string with the number of 1s in the second string. Now I need to accommodate 3 things: whether x and y are equal, or x is greater than y, or y is greater than x. First, let us see the condition that x and y are equal. When would that happen? If x and y are equal, then after swiping all the way to the left, when the number of 1s in x and y are equal, in that case, when we move all the way to the left through x, and after x, when we move immediately to the right, we will be reaching the 0, because we have completely compared x and y and they contain equal number of 1s. All 1s are replaced with x. So after x, will suddenly jump on a 0 which is there in the middle. Once we cross that 0, we need to make sure that there are no extra 1s in the number y after crossing all x's in number x. For that, we will start a transition to make sure that we are skipping all the x's from the given number which is there in the second side. If after passing all x's, we are suddenly reaching to the blank symbol, we can say that the number x and y are equal. The other case is that number x is greater than y. When would this happen? This would happen when I have crossed some number in x, but whenever I am searching the number in y, I suddenly reach the blank. You can see that from Q2, we have a transition on 1 with x replacement to the left. This is actually finding the 1 in y and replacing it with x. But if I am suddenly seeing a blank, that means I have entered the end of the string of the second part, that is y. So that shows that number x is greater than number y. One more case is that number y is greater than number x, or else we can say number x is lesser. When would that encounter? That would encounter when number y is having some number of 1 extra as compared to number of x's. We know that from Q0, when we are reaching 0, 0 transition, that means we have ended the symbol x and we are reaching y. Over here we saw that whenever we are reaching blank symbol along with that, number x and y are equal. But instead, if we are reaching to a symbol 1, that means y is greater than x. Over here, I have constructed the required Turing machine, but I have not declared any state to be the final state. The question says that whenever x is greater than or equal to y, we need to declare that that particular state is final. Three special states I have declared over here is QE, which is the state the string is going to achieve when x and y are equal. QG, which is the state the machine will achieve when the number x is greater than y. QL, which is the state that the machine will achieve when number y is greater than x, or else we can say number x is less than number y. We know that according to the question, state QG and state QE must be final. This completes the construction of the machine. Now let us discuss the components of this machine. We know that a machine M, which is a Turing machine, has the following components. Q, the set of states. Sigma, the set of alphabet. Tau, the set of tape symbols. Delta, transition function. Q naught, which is the initial state. Blank symbol, and the set of final states. Over here, I have used various states. Let us write them down in Q. We have Q0, Q1, Q2, Q3, Q4, Q5. Other than them, QE, QG, and QL. Sigma would contain the alphabet. Over here we are using 0 and 1. Tau would contain the set of tape symbols. Over here I have 0 and 1. Along with that, I have used even the symbol X. We have discussed Q, sigma, tau. Q naught, as we know, is the initial start state. We know that box is used to represent blank symbol. Over here, F is the set of final states. I have declared QE and QG to be final states. Having defined all other components, now let us write down the transition function delta. Let's start with the transition one by one. Delta of Q0 on 1 will be going to state Q1, replacing 1 with X. Let's see the next transition. From Q1, we skip every one and move to the right. From Q1, whenever we encounter 0, that means we have already passed the first number X. So we'll go to the next state. From Q2, all the initial X's in the second number is passed again. Whenever we see the first one, we make it X and move to the left and go to the next state. From Q3, we will again skip all X's and keep on moving to the left. Then we reach the 0, which is again the middle of the two numbers. From Q4, we will skip all the remaining ones in the first number to reach the first one. Whenever we reach X, we need to move to the right to point to the next first one on the number X. Along with that, we go to the initial state Q0. Now we need to write the other transition. From Q2 on a blank symbol, we know that number x is larger as compared to number y, and hence we'll go to the state Qg. Let's write down the remaining transitions. From Q0, whenever we see a 0 on moving to the right, it means that we end with the string x, and hence we need to check whether y is containing any ones or not. If it does not contain any 1, we'll go to the state which represents x and y are equal. Otherwise, we will go to the state QL. From Q5, whenever we see the blank symbol from state Q5, it means that we have cancelled out equal number of ones from both string x and y, and hence we'll go to the state QE. Similarly, from Q5, if we see a 1 at the end, that means that similarly from Q5, whenever see a 1, which means that number y is having exceeding number of ones as compared to number x, and hence we'll have a transition to the state QL. So far, we have constructed the machine and we have defined some of the components. We have seen Q, sigma, tau, we have declared delta, Q naught, blank symbol, and final states. Now, we will try to run three conditions. We'll take two numbers x and y such that x is equal to y, x is greater than y, x is less than y, and we'll see how machine is behaving. Initially, let us take both numbers x and y as unary 4. The representation on the tape would be something like this. It would contain blank symbol from both left and right. Input start with 4 ones, followed by a 0, followed by again 4 more ones. Now, let us use instantaneous description notation to run this particular string with this Turing machine. Initially, the state of the machine would be something like this. Q0 is the initial state, and the tape contains 1 1 1 1 followed by a 0 followed by 4 more ones. Let's try to run this using the transition. Q0 on 1 would replace the 1 with x and move to the right. 1 will become x. New state would be Q1. Remaining symbols would be as it is. Now, next transition would be from Q1 on 1, it will constantly move on to the right by skipping 1. I have completed 3 transitions over here for the first one, second one, and third one. Now, from Q1, we have a transition on 0 to the next state, Q2. This would be the new configuration. X, 3 ones followed by 0, state is Q2. All the 4 ones are as it is in the second number. From Q2 on 1, we'll have the next transition, which will replace the 1 with X. Along with that, machine will move to the next state, Q3, and the string would move to the left. From state Q3 on a 0, we'll have the transition which will go to the state Q4. Along with that, we have a left move. Q4 on 1 would constantly move on to the left. Again, we have 1. We will keep on moving to the left. Again on 1, we'll keep on moving to the left. From Q4 on X, we'll have the next transition to the initial state Q0 moving to the right. In this configuration, from Q0 on a 1, we'll have the next transition to state Q1. We'll replace 1 with X and move on to the right. From Q1, with every 1, we know that we need to skip it and move on to the right. From Q1 on a 0, we'll go to state Q2, moving to the right. From Q2 on X, we'll skip the X and move on to the right, keeping the state as it is. From Q2 on the first one, as we can see in the state, we will replace that 1 with X and keep on moving to the left. Q3 on a X, we'll skip the X and keep on moving to the left. Q3 on a 0 will make the next movement. It will go to the next state, Q4. From Q4, with every 1, we need to skip it and keep on moving to the left. Again, we have encountered a 1. Q4 on an X will keep on moving to the right. Along with that, it will go to the state Q0. You can see the pattern over here. With 2 transition, I have cancelled 2 X's from the left as well as 2 X's from the right. When we continue to pass the string more and more, you will see that finally we'll reach to a state as follows. I'm using a star here to represent that we're using 0 or more number of moves. The configuration would be something like this: X's followed by zeros followed by X's back again. From Q0 on a 0, we have a transition to state Q5. Along with that, we are moving to the right of the tape. From Q5, it will keep on skipping all X's and it will try to find whether there is any 1 or we are reaching a blank. Over here, you will see that after skipping the 4 X's, we will reach to the blank symbol. I'm showing you the final configuration of the machine. From Q5 on a blank, it will go to the next state. Over here, that is QE state. As my Turing machine is achieving a final state after running this string, I can say that this particular string is accepted. Even you can say that x is equal to y is satisfying the condition x is greater than or equal to y. The correction in the machine would be from Q3 on the symbol x, instead of right, we have to move to the left. Because we have already reached the left of the string, that is, we already marked the 1. Now from the second portion of the string, we have to move to the left. Until now, we have solved various questions on Turing machine, such as how can we use a Turing machine to add 2 numbers or to compare 2 numbers, etc. In the next example, we would be saying Turing machine used as a subtractor. There are other applications as well. Later, we'll be discussing on how can we combine Turing machines and make more complex applications. Now, all these things in turns proves that a Turing machine is very powerful In fact, it is as powerful as a computer. In fact, according to the thesis called Turing-Church's thesis, a Turing machine is as powerful as a computer, which means that anything that could be solved using a computer or using an algorithm could be solved using a Turing machine as well. Thank you for watching this video. Stay tuned to Ekeeda and do subscribe.